First of all, I would like to thank the organizers for the kind invitation. It's a really great honor to be here, and Matthew for a very nice introduction. And you did excellent job with the pronunciation of University of Jyväskylä. It's a very difficult Finnish name. So, and thanks for all of you for coming here to listen to what I will talk today. So, in general, I will discuss mainly 3 topics. First of all, to discuss how the state of the catalyst under the electrocatalytic reaction conditions. How does it look? What we can do, what we should do. And then I look at the 2 different electrooxidation reactions, biomass-derived species, glycerol electrooxidation on the gold. How does the pH affect the electrocatalytic activity? And how does the surface species do that? And then another topic is a bit larger, biomass-derived species. It's a glucose, and actually I will also discuss about the xylose electrooxidation as well. And there the key question is to look at the conformation analysis, because this is a big molecule, so how do you know which kind of conformation the molecule may take on the surface? And how does the pH impact on the electrooxidation? This schematic picture from Nerskov and Jaramillo gives nice overview on the potential sustainable ways to make the chemicals that we need in the future and in today. So we basically need nitrogen, water, CO2, and we need renewable energy, and then catalyst. And then we can make the species that we are now producing using the fossil resources: ammonia, hydrocarbons, oxygenates, hydrogen. And this can be then used in a variety of applications where we need them. Today I will particularly focus on the hydrogen and how to speed up or how to improve the hydrogen production. So typically, a sustainable hydrogen production takes place by water splitting, where the hydrogen is produced on a cathode and then the oxygen evolution reaction takes place on the anode. And the amount of energy or electricity that the 1 kilogram of hydrogen production takes is about 40 to 50 kilowatt hours. And that's quite a lot. And 2/3 of the price of the hydrogen is the electricity cost. So the question is that, what can we do to improve the situation? And one option is that instead of looking at the oxygen evolution reaction, we replace the oxidation reaction with another biomass-derived organic oxidation reaction, which hopefully has a lower thermodynamic potential compared to what the water splitting has. And this reaction could be then less energy intensive, which would save also the electricity. And on the other hand, it would also produce something value-added species, not just oxygen, but something that we could make money out of it. And these together would perhaps help to lower the price of the green hydrogen. So like I said, in this talk, I will focus in particular at the glycerol as a monomolecule and then a sugar molecule, organic sugar molecules. And we are looking at these reactions on a gold catalyst. And you might ask, why? I mean, gold is expensive. Well, it is relatively active and selective for these conversions. It's also resistant to poisoning. So you can see on the bottom left picture, the platinum easily makes oxides at the potentials where the glucose electrooxidation takes place. Same applies to the glycerol. So in the terms of the state of the catalyst under the reaction conditions, gold is simple for people to model. But yes, so like I said, we will look at use the first principles calculations. And now the question is, how do we model this electrochemical interface? How does it look at the atomic scale? Marco Melander made this very nice picture into his paper, and I borrowed from there. So what components do you have there? You have the electrocatalyst, you have the solvent, electrolyte, you may have pH effects, you have a chemical reaction or electrochemical reaction, you have electrons coming from the external source, you have different kind of interactions and processes. So do we need to include all of this complexity when we do the modeling? The answer depends what you are looking at. So there are different kind of models depending on for the interface. And now you either include just the catalyst, metal slab in DFT calculations, or you start increasing the complexity and including the solvent. It might, in the first step, be including one water molecule or a couple water molecules, or you might be using implicit solvent or a combination of implicit solvent and explicit water molecules. Or in the very end, you just use explicit water. But of course, going from left to right increases the computational cost. So you need to think twice what to include into your model. And actually, I will come back to this point at the end of my talk. To raise this question again, is one approach better than the other one? Yes, it depends what you are looking at. So if we start from the leftmost model, the very simple model to use in a computational electrocatalysis, it's the famous computational hydrogen electrode approach, which celebrates its 20th birthday this year, developed by Jens Nørskov and co-workers. And this approach is based on the assumption that under standard conditions and defining zero voltage of the standard hydrogen electrode, there is an equilibrium between the half of the hydrogen molecule and the proton-electron pair, which means that the free energy of H2 computed in the gas phase can be used to determine the energy of the proton-electron pair. So this is a fantastic approach. And therefore, for reactions involving simultaneous transfer of proton and electron can be written according to the equation on the bottom. And the computational hydrogen electrode approach has been tremendously successful during the past years. For example, screening for active catalysts for different electrochemical reactions, understanding selectivity competition between, let's say, nitrogen reduction and hydrogen evolution reaction, or identifying the atomistic reasons for experimental efficiency limitations for different reactions. It's easy to use, it doesn't need any modifications to your DFT software, and it works nicely for thermodynamics, but for kinetics, it doesn't. And here is the example of a problem why constant potential calculations are needed. So this is a Hirosky reaction on a platinum surface, which has a full monolayer of hydrogen. And Karen Zhang and Jens Nørskov, they computed the barrier for the reaction. And what they observed is that the potential, that is the Fermi level, is changing over 2 volts during the reaction barrier calculation. So thus, this kind of calculations do not mimic the experiments where the potential is fixed. And we need something else to carry out the constant potential kinetic calculations. And that's something else that we've been using and developing a little bit. There are other groups who have done excellent work on this. is this grand canonical ensemble or constant potential DFT. So the electrode potential is equal to the electrochemical potential of electrons in the electrode. And this table summarizes, I would say, the key differences between these two approaches from the perspective of how to use it. So if you have a constant potential DFT calculation, your electrode and electrolyte chemical potential is fixed, but you vary the number of electrons. So your input parameter is the potential that you're targeting at, and then you adjust the number of electrons to meet this potential. In a canonical or normal DFT, it's vice versa. So the electrode potential is varying, as we saw from the example on the previous slide, but the number of electrons is fixed. And if you do the constant potential DFT calculations, you will have grand free energies, which consist of the total energy of the DFT, plus the term that includes the absolute electrode potential times the number of electrons. And then you can carry out the energy difference calculations, like shown here in the equation. And the absolute potential, or absolute electrode potential, mu E, it's a Fermi energy referenced to the electrostatic potential in the solvent. That's the typical approach to do grand canonical DFT calculations. And that's also what we have done in the examples I show later. And here on the bottom, I show an example of the grand canonical DFT calculations. This is the Volmer step barrier calculation for the graphene modified with the nitrogen and having a ruthenium atom. And you can see that when you do the DFT, grand canonical ensemble DFT calculations, you get the potential-dependent barriers, and of course the reaction energies. But this, how do you do the constant potential DFT calculations? It's not unique. So in the examples that I will discuss today, you do it by fixing or choosing the Fermi level, so choosing the absolute electrode potential that way. We have recently developed an alternative approach to carry out the grand canonical ensemble DFT calculations. And majority of this work, or mainly, has been carried out by junior group leader Marco Melander at our university and department. And constant inner potential approach, it uses the local electrode inner potential as the thermodynamic parameter for the electrode potential instead of the global Fermi level. So we use the electrostatic potential of the material. And it has certain advantages. So the SIP method and Fermi level constant potential DFT method, they are equivalent for metal systems and inner sphere reactions. But the SIP approach works also for outer sphere reactions and the two-electrode system. And I have an example here about the two-electrode system and the molecular junction between the electrodes. So the Fermi level approach, it's not the Fermi level of left or right electrode, it's the Fermi level of the system. So this Fermi level-based constant potential DFT calculations cannot calculate the potential difference between the two electrodes. But this is what the SIP approach can do, as well as looking at this kind of molecular junctions or outer sphere reactions where you have an outer sphere complex on, let's say, on a metal surface. The electrode potential should be the metal surface electrode potential, but the Fermi level easily lies in an outer sphere complex. And then it doesn't mimic the experimental situation. But this is something that we published earlier this year, and like I said, we have used this fixed Fermi level approach. So maybe one of the first studies published on the constant potential DFT is this work by Georg Kastluge and Andrew Peterson, where they look at the Volmer step on gold and platinum surface and computed the barriers, not only the thermodynamics. And this result, as expected, confirms that the platinum is better catalyst than gold. It has much lower barrier. And you can see how the barrier depends on the potential. Now, the disadvantage of this approach, this computation, grand canonical ensemble DFT, is that it's computationally more expensive than normal DFT and computational hydrogen approach. And for each of these different potential calculations, you need to run a separate DFT calculation. So, and moreover, it requires modifications to your software. But it also allows to make you the Pourbet diagrams, which shows the variation as a function of pH. As shown in this example, on the left you have a Pourbet diagram computed with the computational hydrogen electrode, and on the right with the grand canonical ensemble DFT. And you can clearly see how the pH dependence go. Now I move on to the glycerol electrooxidation on a gold 111 surface. And this is the reaction that has been extensively studied in the literature by, for example, Mark Korber and co-workers. In general, what is observed is that under alkaline condition, gold is an active catalyst, and glyceric acid is the main product. And it's known, but not quite identified, that the surface OH species are important for this reaction. However, under acidic conditions, gold is inactive. Maybe some small amounts of dihydrogenacetone are seen in perchloride ions, so in the presence of a certain type of electrolyte. And now our question was that, how do we understand this pH dependence? We start with looking at what is the state of the catalyst under the electrochemical reaction conditions. And this is now why it's nice that gold is simple, because it does not oxidize on the potentials where the electrooxidation of glycerol or sugars take place. So we don't need to look at the coverages of oxygen or surface oxide formation. It's enough to consider that how much there is OH present on the surface. And for these Pourbet diagrams, we carried out the grand canonical ensemble DFT calculations. The experiments say that under acidic condition, OH adsorption starts at about 1 volt versus reverse hydrogen electrode. Whereas under alkaline conditions, it starts about 0.6. And the maximum is reached, a maximum 0.5 monolayer is reached about 1.3 volt. The onset potential of glycerol electrooxidation is around 1. And it's shown by the dashed line in the plot. So here are our calculations. So we carried out separate DFT calculations for each OH coverages and for each possible voltage values. Then we did some interpolation, so we got the continuous plot. And what we see that at pH 1, the surface is clean up to the voltage 1.35. But with increasing pH, 1/4, 1/3, and half a monolayer of OA adsorption become more stable. And what you can see, the stability of the OH groups increases with increasing pH, and this is known as non-Nernstian shifts, and which originates from the shift in the zero potential charge as a function of the surface dipole. At the alkaline conditions, so around pH 13, 1/3 monolayer is stable at 1.29 volts, whereas a little bit higher voltages are needed for half a monolayer. So if we compare the calculated stabilities to the measured ones, we see that the predictions are kind of okay, but our calculated potentials are higher. Now you need to keep in mind that we have the normal DFT functional issues here, and that we have used the implicit solvent. So considering those facts, I think this match is rather good. Now, why gold is very simple and nice? Well, you learn that when you do platinum 111 surveys. I think my postdoc Laura Laverty carried out around 100 different calculations for OH, hydrogen, and oxygen overlayer structures. And in the middle, you have a plot where each solid line corresponds to a different coverage of oxygen, hydrogen, or OH. And then the dashed line indicates what is the most stable phase. It's difficult to see what is it. So on the right, you see the dark blue line shows that what is the most stable structures at pH 13 at different potentials. So we start with the empty surface, then we have OH groups, then we have OH and oxygen, and finally we have our oxide. If you wonder what is the purple one, that actually mimics if we structure that we have when we destabilize the oxygen by 0.1 eV. This could mimic the error, DFT error in the functional, or it could be introduced by implicit electrolyte ion effects. You can pick which one you look. But this shows that how sensitive these structures are. Anyway, it shows that on a platinum surface, the overlayer structure is much more complex. And if you look at the electrooxidation of glycerol on that surface, the calculations becomes a bit more tedious, as we have observed. Now, glycerol electrooxidation, under acidic conditions, we form dihydroxyacetone, so DHA is the main product. However, it can also form the glyceraldehyde GLD. So the question, these two pathways are competing, and the question is that which one is winning based on the calculations. So here is the energy landscape. So these calculations have been carried out with the normal DFT plus implicit solvent using the computational hydrogen electrode. And you might wonder that why on earth did you do that when you have this constant potential DFT calculations? These calculations were carried out some years ago, so at that time we had less experience on the constant potential DFT calculations and perhaps less computer time as well. And what these results show is that the electrooxidation of a glycerol is energetically highly unfavorable. In particular, the barrier is about 1 EV. Now you might wonder that, okay, you showed the plot which highlighted how the voltage varies by 2 volts during the simple Herovsky step. Here we checked after calculating these barriers that how much the potential varies, so how much the Fermi level is varying, and it's in a reasonable range, so no 2 volts. So since the barriers are so high, 1 volt, so around 100 kilojoules per mole, this indicates clearly why the gold is non-reactive under acidic conditions. But which one is winning? Is it the DHA or GLD species? And for that, we carried out the typical limiting potential analysis, so looking at their potential-dependent thermodynamics under acidic and neutral conditions, so using the DFT and computational hydrogen electrode. And what we see, and when we compare the limiting potentials, so the blue lines, that for the DHA, the limiting potential is about 0.17, while for the GLD, it's about 0.6. So it clearly, the potential favors the formation of DHA, supported the experimental findings, which indicate that only DHA is possible under acidic conditions. Now, what happens when we move to the alkaline conditions? Now we have OH species on the surface, and if you look at the numbers under the arrows, the first number is the activation barrier, and the second number is the reaction energy, and suddenly they are much lower than what we observed on the bare surface. And the other observation that we have is that the GLD formation is competitive with the DHA. However, experiments indicate that the glyceric acid, so GLA, is the main product, and there is no electrocatalytic pathway from DHA to GLA. So what we think is happening there is that there is a tautomerization from DHA to GLD, and that's happened to be more favored under alkaline conditions. So it doesn't matter if we form DHA, it can tautomerize the GLD, which can then react to the acid. And the reactivity is much higher now. And it's due to the fact that the OH group on the surface actively participates to the reactions. It stabilizes the species and lowers the activation energies. Our mechanism indicates that this is entirely surface-driven process, but there are experimental evidence by Mark Hooper and co-workers that the solution phase OH minus might deprotonate GLY to GLD1, so glycerol to reactive intermediate, which then adsorbs and reacts. So that this reaction would be partially surface-driven and partially solution-driven. So here you see the structures. We have the organic species, and then we have actually 2 OH species on the surface. Now you might wonder that, wait a second, didn't she earlier say that you need a higher coverage of OH species on the surface? Yes, you do need, or based on the Bourbeil diagram, you have more OH groups on the surface under reaction conditions. However, more OH groups on the surface makes calculations more tedious because there are more freedom. So therefore, we were trying to minimize the computational cost and the time, and we were testing that how little OH we need for the surface. And we tested this for the one reaction, for one CH bond-breaking reaction. And here you see that what is the reaction energy and what is the barrier if we compare the per surface with respect that we have either 1, 2, or more OH groups on the surface. And you can see that, okay, broadly speaking, having 2 OH groups on the surface is enough to introduce the effect and keep the computational burden reasonable. 1 is not enough. So what we see is that you need 2 OH groups. 1 is just hanging around and 1 is actively participating. If you have more, you just introduce more trouble to yourself. My second example is sugar electrooxidation. I have written down glucose, but I actually say a few words about the xylose as well. Here the calculations, we focus entirely on thermodynamics, and you will see soon why, but all these calculations have been done on a level of grand canonical ensemble DFT, unlike the glycerol reaction thermodynamics and kinetics, where we apply the computational hydrogen electrode. And we use the implicit solvent. Our experimental colleagues in Åbo Academy, in group of Henrik Grenman and his PhD student J.P. Ona, who happens to be here in the audience, they carried out experiments on glucose and xylose electrooxidation on a nanoparticle cold catalyst supported on a carbon. And then they approached us to ask that, okay, we would like to understand what's going on. And what they see is that when the current increases around 0.5 towards anodic direction, the potential increases, so the anode current appears, and there is a peak around 1.5. And this peak is about the same for both sugars, and it has been previously linked to the glucose electrooxidation to gluconate. This slide summarizes the proposed reaction mechanism for glucose electrooxidation, and actually the same mechanism has been proposed for the xylose. So first step is the isomerization. This is the thermodynamic step. Then you can break the carbon-hydrogen bond, or you can break oxygen-hydrogen bond. But anyway, you will end up to gluconolactone, which is this species here, which can either oxidate on a surface-mediated process, the gluconate, or it can desorb to the solution phase and oxidize there. And then the final step to the gluconic acid takes place on the solution phase. Now the question that we were trying to answer is that what is the role of OH species? Because again, for these sugar molecules, it was seen that their alkaline conditions are more favorable than acidic conditions. And is the presence of OH groups related to the a higher activity? But now we are dealing with a much larger molecule than glycerol, and we need to look for the conformations. So we use the dock-on-surf software to generate different conformations, first in the gas phase, where we then optimize them with the not very accurate DFT approach, then kept the 20 most lowest one, fully optimized them with more accurately in the presence of the solution phase. Then we selected 2 to 3 example configurations for each molecular configuration and placed them on a surface. And again, using dock-on-surf found the configurations, a different kind of adsorption configurations. And then stepwise optimized the best conformations. This way, we think that we have more or less relatively stable optimized structures for the reactants and intermediates and the products. Population analysis shows that in the solution phase, the alpha tautomer is favoring over the beta in line with their experiments. On the surface, it's the beta that is favored on the bare gold and the alpha that is favored on the hydroxylated sulfur. And then the fructose, that is the isomer, is also showing the different populations. Unfortunately, the fructose populations do not match the experimental ones. What we observe here is that the presence of the OH groups substantially stabilizes the species compared to the bare surface. You can see that it's about 0.2 to 0.4 EV more stable. So you can imagine that perhaps, or think that perhaps these OH groups already do something. Okay, I will skip the xylone because the story is more or less the same. Here is the thermodynamic potential energy landscape, now calculated at the level of the grand canonical ensemble DFT. And what we see, I don't go to all the details, but on the left you have the bare surface, on the right you have the surface with the OH groups, and then you have 2 different tautomers. First of all, we see that the isomerization is preferred to the fructose. However, this is a chemical step, so it's not depending on the potential, unlike you see that the sugar oxidation is in. And C1 deprotonation is favored over the OH deprotonation. And what we see that these thermodynamic barriers for the first 2 proton-coupled electron transfer steps, they are energetically closer to each other on the hydroxylated surface. In the presence of the OH, the lactone desorption is less favored, and we find that the gluconate formation is a potential limiting step. So here are the potentials. What we see here is on the surface-mediated here on the left, and then the solution-mediated. You remember the final part of the mechanism. It can take place either on the surface or in the solution phase. And now we see that on a surface case, the limiting potential is about 1 volt for each case. Whereas in a solution phase, we have much lower limiting potentials. Varies a little bit between the 2 tautomers. It's either 0.64 or 0.42. So it looks like the solution phase is thermodynamically more favorable. But if we look back to the reaction mechanism, so now the question is how we proceed from here onwards. Shall we continue on the surface or shall we go to the solution phase? So this step, going from gluconolactone to gluconate, it's based on the calculation, the potential limiting step. And the absorption to the solution phase of the gluconolactone is actually favorable. Moreover, going from gluconolactone to gluconate, there must be a kinetic barrier for the ring opening. But we did not calculate any barriers because that's far too expensive to do computationally. These are big molecules, so I don't even want to think how to carry out all these constant potential DFT barrier calculations for this size of the molecule. Now, based on the experiments, it's said that it's actually this step that is the potential limiting step. So the first, the proton-coupled electron transfer. Moreover, the experiments from a group in Åbo Academy, they said that the diffusion is kinetically limiting this process. So we think that at this point, the gluconolactone desorbs to the solution phase and the reaction completes there. However, if the potential is higher, then it's possible that the surface reaction takes place. The problem there is, or the challenge, that the desorption of the gluconate is a reduction process, so it becomes less favorable at the higher reducing potentials or higher pH. So there is maybe a small potential window when this reaction is also possible. So they can compete, basically. But I would say that based on the calculations, we have both surface part of the reaction and then the end, it continues in a solution phase. And now imagine we did the calculations with the implicit solvent model. So yeah, that's a limitation. The story is pretty much for the xylose, so I don't go into the detail for the sake of the time. So this brings me to the end. So what I'm trying to tell you today is that this, from the atomistic perspective, these electrochemical interfaces are very complex. And understanding the reactions and different constituents of this interface from the experiments alone is difficult, so you need calculations. However, you can do the calculations with using different kind of DFT methods and different kind of atomistic models for the interface. And you don't necessarily need always the most computationally demanding approach to achieve the calculations, to achieve the answers to your question. So we have been developing and now more and more using this constant potential DFT approach because it gives us both the thermodynamics and kinetics. But it's computationally more costly than the normal DFT. And these examples highlight how the OH groups on the surface of a catalyst influence the activity and the selectivity of the electrooxidation of biomass-derived species. But both examples indicate that the solvation phase may play a role. So this brings me back to my slide where I showed this kind of different solvent models. And yes, it would be beneficial to use some explicit water molecules in these calculations. However, we cannot have it all, so these constant potential DFT calculations are already computationally so costly that one needs to cut corners somewhere. But now I would maybe include a couple water molecules to see if they have an effect, if I would do these calculations or some of it again. And finally, I want to thank the people who have been contributing this, Marco Melander, who is the junior group leader, and my postdoc, Laura Laverdew. She's about to leave my group soon, so she's looking for new positions. So if you want somebody who can do this kind of calculations, send her a message or contact me so I can tell her. And then my former postdoc, Anat and Dongwei. And then, of course, our experimental collaborators in Åbo Academy, and the funding and the computer time, and you for your attention. Thank you.